Geographic Information System, Lesson 13, Data Query. In the previous chapter, we have discussed about different data quality issues. We have discussed about different accuracy types and how it is important in determining credibility of the data with respect to the real world phenomena. We have discussed about precision and different types of resolution. In this chapter, we will discuss about how the data can be queried from GIS database and helps in examining the relationship between the data sets. Objectives. One of the defining characteristics of GIS is the ability to ask questions and get answers in spatial context. These questions or queries are requests for information that are posed in specific fashion. In this chapter, we will discuss about data query, map-based data manipulation, attribute data query, spatial data query, raster data query. More recently, the data visualization has emerged as a discipline that uses a variety of exploratory techniques and graphics to understand and gain insights into data. Similar to statistics, data query in GIS lets say user view the general patterns in the data set, query data subjects and hypothesis about possible relationships between data sets. But there are two important differences. First, data exploration in a GIS involves both spatial and attribute data. Second, the media for the data exploration in GIS includes map and map features. For example, in studying the soil condition, we want to know not only how much the study area is rated poor, but also where those poor soils are distributed on the map. Therefore, besides descriptive statistics and graphics, data query in GIS most also cover map-based data manipulation, attribute data query and spatial data query. Today, we will be talking about how to get more information from your data once you have it in your GIS. The simplest method of the further analysis is through querying. Although straightforward, it can however form a powerful tool in the extraction of pattern and meaning from our data. Within a GIS, you can query data in two ways. Firstly, you can perform standard attribute queries as you might in any other database software. Secondly, you can also perform spatial queries, more on which later. Data query. Queries are expressed in a formal way using structured query language SQL. This language is composed of a set of commands and rules that are used to ask questions of a database. SQL, which has been implemented for nearly every DBMS, comes in many subtly different flavors depending on the database being queried. However, the details of these differences are not a concern when using ArcMap application in ArcGIS desktop. The software detects the characteristics of the underlying database being queried and modifies the interface. So, SQL statements will be created using the appropriate search terms and information. The user is not required to understand the SQL format for the specific database being queried. There are two types of queries, attribute and location. Attribute queries ask for information from the tables associated with features or form standalone tables associated with GIS. Attributes can be numeric values, text strings, Boolean values, that is true or false, or dates. This kind of query is similar to a query made to an database. However, when using a GIS, the answers, that is the features related to the records selecting by the process, are highlighted on the map as well as in the table. The answers to spatial queries are derived directly from the location of features on the map. Information about the proximity of one parcel to other parcel or other kinds of features such as roads is not contained in an attribute table, but is easily learned using spatial query. For example, you could ask if one or more features are located within a certain distance of a feature, are contained by another feature, intersect other feature, or possess another of the relationships defined by spatial operators. GIS is powerful because it can use both attribute and spatial queries to get answers with far less effort or answer questions that would not be practical to answer using any other method. Building a basic query. All basic queries have three parts: source, filter, and relationship. This is true for both attribute and spatial queries. The source can be a table or feature class. The filter can be an attribute value or a shape or feature. The relationship between the source and filter is based on logical comparison and spatial operators. Graphs. Different types of graphs are used for data exploration. Graphs may involve a single variable or multiple variables, and it may display individual values or classes of values. An important guideline in choosing a graph is to let the data tell the story through graph. A line graph displays data as line. A bar chart, also called as histogram, a group of data into equal intervals and uses bars to show the number of frequency of values falling within each class. A bar chart may have vertical bars or horizontal bars. A cumulative distribution graph is one type of line graph that plots the ordered data value against the cumulative distribution values. A scattered plot uses markings to plot the values of two variables along the x and y axis. Bubble plot are a variation of scattered plots. Instead of using constant symbols as in the scattered plot, a bubble plot has varying size bubbles that are made proportionate to the value of the third variable. Box plot is also called the box and whisker plots. Summarized distribution of 5 statistics form is data set that is the minimum, the first quartile, median, the third quartile, and maximum. Some graphs are more specialized like quantile plots, also called QQ plots. Compare the cumulative distribute of the data set with that of some theoretical distribution such as the nominal distribution bell-shaped frequency distribution. Most GIS packages provide tools for making graphs and charts. ArcGIS, for example, has a chart engine that offers bar graphs, line graphs, scattered plots, scattered plot matrix, block plots, and pie charts for mapping as well for exporting to other software packages. Map-based data manipulation. A recent development in data visualization is geovisualization, focusing on geospatial data and integration of cartograph image analysis, and exploratory data analysis. Maps are important part of geovisualization. Data manipulation uses maps including data classification, spatial aggregation, and map compressions. Geographic visualization used to focus on the use of the map for setting up a context for processing visual information and for formulating research questions or hypotheses. A number of software packages have been developed specially for geographic visualization such as Explore Map and Common GIS. Recent development have broadened the scope of geographic visualization and introduced the new term geovisualization. Geovisualization emphasizes the integration of cartography, GIS, image analysis and exploratory data analysis for the visual exploration, analysis, synthesis and presentation of geographic data and for spatial decision support. Data classification. Data classification can be a tool for data exploration, especially if the classification is based on descriptive statistics. Classified maps can be linked with tables, graphs and statistics for more data query activities. Spatial aggregation is functionally similar to data classification except that it groups data spatially. Because of geographic units from a hierarchical order, we can explore an effect of spatial scaling by examining data at different spatial scales. If distance is the primary factor in the study, spatial data can be aggregated by distance measurement from point, line or area. Spatial aggregation for raster data means aggregating cells of the input raster to produce a coarser resolution raster. Map comparison. Map comparison can help a GIS user sort out the relationship between different data sets. Comparing layers that are polygon or raster layer is difficult. One option is to turn these layers on and off. ArcGIS has a swap tool that can show what is underneath a particular layer without having to turn it off. Another option is to use transparency. Thus, if after the layers are to be compared, one layer can be displaced in the color theme and the other in the semi-transparent. The grey shades simply dark in the color symbols and do not produce confusing color textures. If the layer to be compared represent temporal changes of their theme, they can be viewed in animation. Attribute data query retrieves a data subset by working with attribute data. The selected data subset can be simultaneously examined in the table displayed in charts and linked to the higher lighted feature on the map. The selected data subset can also be printed or saved for further processing. Attribute data query requires the use of expression which must be interpretable by GIS or a database management. The structure of these expressions varies from one system to other, although the general concept is the same. ArcGIS, for example, uses SQL for query expressions. In ArcMap, the query operations use SQL. If the data set is added, your database feature class, but limited version of SQL if the data set is a coverage or a shapefile. Therefore, a geodatabase feature class allows greater flexibility and more query option than a coverage or a shapefile. Additionally, the notation can be different. For example, the fields in the query expression have square brackets around them. If the fields belong to a geodatabase feature class but have double quotes if the fields belong to coverage or a shapefile. Attribute queries effectively take the form of a question. The easiest way to conceptualize this is that you are constructing a sentence using a special syntax that will select a subset of your data as a result. In ArcGIS, this type of query is constructed using the select by attribute tool. As you will be able to imagine, as the size of your database increases, this tool becomes more and more useful. The results of a query can be exported either as a new layer or as a data table. This allows us to query our data using the GIS and then export the results for further analysis in the external software, perhaps to perform statistical tests. However, usually we could perform this type of query in our external software in any event. The real strength of GIS lies in constructing spatial queries. type of operation. Attribute data query begins with a complete data set. A basic query operation selects subset and divides the data set into two groups, that is, one containing the selected records and other unselected records. Given a selected data subset, three types of operation act on it: adding more records to the subset, removing records from the subset, select a smaller subset. Operations can also be performed between the selected and unselected subset. We can switch between the selected and unselected subset, or we can clear the selection by bringing back all records. These different types of operation allowed greater flexibility in data query. Relational database query works with a relational database which may consist of many separate but interrelated tables. A query of a table in a relational database not only selects the data subset in the table but also select records related to the subset in one table. This feature is desirable in data exploration because it allows the user to examine related data characteristics from multiple linked tables. To use a relational database, we must be familiar with the overall structure of database, the designation of keys in relating tables and data dictionary listing, and describing the fields in each table. For data query involving two or more tables, we can choose either to join or relate the tables. A join operation combines attribute data from one or more tables into single data. A relate operation dynamically links to table but keeps table separately. When a record in a one table is selected, the link will automatically select and highlight the corresponding record or records in the related tables. An important consideration in choosing a joined or related operation is the type of relationship between tables. A joint operation is an appropriate for the one-to-many or many-to-one relationship, but in operate for one-to-many or many-to-many relationship, a relate operation on the other hand can be used for all four types of relation. Spatial data query. The spatial data query refers to the process retrieving a data subset from a layer by working directly with feature geometrics. Results of a spatial data query, like those of an attribute data query, can be simultaneously inspected in the map, linked to the highlighter records in the table, and displayed in the charts. They can also be saved as new data set for further processing. To select features spatially, a cursor, a graphic, or a spatial relationship between features can be used. Feature selection by cursor. In the simplest spatial data query, to select a feature by pointing, edit, or to select feature by dragging a box around them. Feature selection by graphic. This query method uses a graphic such as a circle or a box, a line, or a polygon to select features that fall inside or are intersecting by the graphic object. We can use the mouse pointer to draw the graphic for selection. Feature selection by spatial relationship. This query method selects features based on the spatial or topological relationship to other features. Features to be selected may be in the same layer as a feature for selection, or more commonly they are in different layers. Spatial relationship used for the query include containment. Containment selects features that fall completely within features for selection. Example including finding schools within a selected country and finding state parks within a selected state. Intersect. Intersect selects features that intersect features for selection. Example including selecting land parcels that intersect a proposed road and finding urban areas that intersect an active fault line. Proximity. Proximity select features that are within a specified distance of features for selection. For example, including finding state parks within 10 miles of an interstate highway and finding grocery shops within 1 mile of selected street. If features to be selected and features for selection share common boundaries and if the specified distance is 0, then proximity becomes adjacency. In ArcGIS, spatial queries are performed using select by location tool. Again, with this tool, we are effectively constructing a sentence by selecting the sentence terms using drop-down boxes. The variety of different spatial queries can be performed using this tool is quite staggering. There are many different types of spatial query built into this tool, reflecting the many different kinds of topological relationship that any two geographic objects might possess. Beyond distance form, this includes intersection and crossing, partial or complete containment, shared line segments, equivalence, boundary touching, etc. The use of this tool is an excellent way of exploring your data. Finally, it also is possible to make selections manually in ArcGIS using the appropriate tool, and a further tool provides the ability to recover objects recorded by clicking on them spatial analysis. Of course, beyond simple querying, there are also a whole host of more involved methods of spatial analysis made possible using GIS. In ArcGIS, the standard variation of these tools are accessed through the red arc toolbox icon or from various toolbars. There are also many scripts and tools for ArcGIS written by other users that can be downloaded from ISRI website. The provision of user generated content is also excellent if you are using GRASS, especially when seeking tools for raster analysis. From an archaeological perspective, many of these tools have been used successfully by members of our discipline. Raster data query. Although the concept and even some methods for data query are basically the same for both raster and vector data, there are enough practical differences to wear into the separate sections on the raster data query. Query by cell value. The cell value in the raster represents the value of a continuous feature at the cell location. Therefore, to query the feature, we use the raster itself rather than a field in an operand. One type of raster data query uses a Boolean statement to separate cells that satisfy the query statement from cells that do not. Raster data query can also use the Boolean connectors of AND, OR and NOT to a string together separate expression. Querying multiple rasters directly is unique to a raster data. For vector data, all attributes to be used in a compound expression must be from the same table or tables that have been joined. Another difference is that GIS package such as ArcGIS has dialogues specifically designed for vector data query but does not have them for raster data recovery. The user interface for raster data query is often mixed with commands for raster data analysis. Query by select features. Features such as point circle boxes or polygons can be used directly to query a raster. The query returns an output raster with values for cells that correspond to the point location or fall within the feature for selection. Other cells on the output raster can carry no data. Again, this type of raster data query shares the same user interface as commands for data analysis. Summary. Whether the question to answer is simple or complex, break down the question being asked into its query components, source, filter and relationship, and arrange those components in the order that correctly and efficiently answer that question. Understanding the data distribution in a data source will also help you understand how to best order operation to minimize the number of records that must be searched. In this chapter, we discussed about different data query method, that is attribute data query, spatial data query and raster data query. Provides an additional complex layer based on the requirement of the GIS user. Data query helps in understanding the database and helps GIS report making in decision support system.